I feel like I got the memo that I canceled. Didn't get the memo that I canceled class or something. Well, there's a few people here. Questions at all over anything? Things going all right? Okay. Well, let's continue our discussion with linear independence that we started last time. So remember that linear independence means that if we have a set of vectors v1 out to vn, and we say it's linearly independent, the definition for linear independence is that if you have a linear combination that gives you the zero vector, then what has to be true about your constants? If you have for linear independence, if you have a linear combination that gives you the zero vector, what has to be true about all the constants? Do I have one of these? Probably somewhere. Nope, that's not it. That's the one I'll hand out later. Somewhere in here. It. Oh, where is it? Apparently I don't have a link. I'm sorry. Anyway, what is true about the constants if you have a linear combination that gives you the zero vector? What has to be true about the constants? What is it? They have to all be zero. I have an extra one. So all the constants have to be zero. All right, so what I ask next on this sheet here is, yes?
Why couldn't you have vectors in the opposite directions?
Then it wouldn't be linearly independent. That's the whole point, is that I can't write one vector in terms of the other. So if you had, say your C1 wasn't equal to 0, okay, then I could solve for the V1.
Right, I'm just saying if V1 was 1 and 2 and V2 was -1 and -2.
Then they're not linearly independent.
I know.
Yeah, so in that case, they would be on the same line. That's the whole idea. They don't give different information, is the idea. Because they're on the same line. So if I did all the scalar multiples of the first one, I would get the exact same set as if I did all the scalar multiples of the second one. I would get literally the same set, which we don't want for linear independence. Got some big smear on my glasses. So that's what we do not want for linear independence. That's the idea. So if I add a new vector to the set, it actually adds new information. So that's the idea. So, for example, just the easy example is that if I have 1, 0, 0 and 0, 1, 0 and did all the possible combinations of that, I get the XY plane, right? So basically I get anything here that's x, y, comma 0, because I can write that as x times 1, 0, 0 and y times 0, 1, 0. Okay. If I want to create something new, I need to make sure I put something in that last coordinate, right? Because if I don't put something in that last coordinate, I'm still in this plane, so it doesn't add any new information. So if I want new information, I got to put something that's a non-zero third coordinate. That's the idea. All right. Yes. I said if C1 is not 0, then it would be, because I could solve for V1. if this C1 is not equal to 0, then I can divide by it. Right? So all I did was just subtract the other ones to the other side and then divide by it. I subtracted to move it to the other side. Right? I have a plus C2 on this side. If I move it to the other side, it's going to be negative. I just literally just solve for if the C1 is not 0, then I can solve for it, which means that if I think this is what I was mentioning over here in the plane. My xy over here, if I tried to throw x, y, 0 in there, pardon me, then I know that I could use x times this plus y times this minus that gives me the 0 vector, doesn't it? Well, then I could solve for any of these. As long as my x and y aren't 0, I could solve for any of these in terms of the other. And so it's not giving me anything new because I could already write this vector in terms of the other two. That's the idea. So I don't need it. If I can already write it in terms of, if I could already write this vector in terms of these two, then I don't need to throw it in my set as something extra. It'll make more sense when we start talking about trying to generate spaces from a finite set of vectors. Okay. All right. So this kind of leads us into one of the reasons why we care about linear independence. So let's say I have, pardon me, let's say I have one vector that I can write in term as a linear combination of my v's. So let's say I have a set of vectors v1 to vn, and I can write my linear combination, or write my vector w as c1 times v1, c2 times v2 up to cn times vn. Do the same thing, but use d1 of dn. Can you give me a linear combination of the v's that gives you the 0 vector from this? What can I do with these equations to get a linear combination of the v's that gives me the 0 vector? What do we need to do? I want to get 0 on this side. What do I need to do? Yeah, just subtract them, right? Just subtract the equations. Exactly, right? Just need to subtract. So we subtract the two. We get 0 on this side. We would get like terms. And so to have C1 minus D1 V1 plus C2 minus D2 V2 out to Cn minus Dn Vn. If my vectors are linearly independent, if I have a linearly independent set, then what has to happen? What has to be true about all the constants? If it's linearly independent, what does this constant have to be? And what does that constant have to be? And all the way out, right? So what does that say about your C1 and D1? They're the same thing. What does it say about your C2 and D2? They're the same. And all the way out, right? Your Cn and Dn have to be the same. So what this says, this is why we care about linear independence. If, and I'll write it off to the side. I'm running out of room to write it underneath it because of the other stuff that I wrote. If I have a linear combination of a vector and the set the vectors that I'm using are linearly independent, then there's only one way to do it. It's unique. The representation is unique. Okay? So to write it out this way, if your set is linearly independent, then every different linear combination yields a different vector. Let me give you an example of what I mean if they're not linearly independent. So, oops. Let's say I have the set 1, 2, and the set -1, -2. That was the example you said earlier, right? Okay. I could write the vector 2, 4 as what? Can you tell me a way to get 2, 4 out of that? I could do 2 times 1, 2, and 0 times the other one, right? Is there another way to do it? I could just say, yeah, subtract the 2. I could 1, 2, and then minus the -1, -2, right? There's 2 ways to do it, isn't there? There's actually infinitely many ways, but there's 2, right? It's not a unique way to do it, correct? Versus if I have the set 1, 0, and 0, 1, and I ask you to write the vector 2, 4 as a linear combination, what do you have to do? Yeah, 2 times the first and 4 times the second, and that's it. You can't do it any other way, right? Right? There's only one way to do it. So if they're not linearly independent, then I can find multiple linear combinations that give me the same vector. But if they're linearly independent, there's one and only one way to write the linear combination. And that gives us, and that later on, that's going to give us ideas of coordinates. Okay. All right. So that's the big deal for linearly independent. It tells you that if you have a linear combination, then it has to be unique. So remember that we did spanning sets before we talked about linear independence. Spanning sets said that I can write every vector in the space as a linear combination, right? There's an existence part. Linearly independent is the uniqueness part. So if we put them together, then you get everything can be written in exactly one way. And that's where we're headed for the next section. All right. Before we get there, let's see if we can do a few theorems. All right. So the first theorem says that any set that contains the 0 vector has to be linearly dependent. Okay. Why is that true? Remember, linearly independent says that if I have a linear combination that gives me the 0 vector, then all of the constants have to be 0, right? So say you have V1, V2, out to Vn, and then I put the 0 vector in there. Can you give me a linear combination that equals the 0 vector where not every single constant is 0? I can multiply the 0 vector by anything I want. So maybe I'll multiply it by 1, say. And what can you multiply every other vector by? 0, yeah. I can do 0v1 plus 0v2 plus 0vn plus 1 times 0. And I get the 0 vector, don't I? That's certainly true. Remember, for linearly independent, it doesn't say they all have to be non-zero. It says for linearly independent, it says that if you have the 0 vector, then all of them have to be 0, right? If at least one's not 0, then it's false. So notice here, even though all of those constants are 0, that one's not, right? Because I can always use any constant I want to multiply times the 0 vector, and I get 0. So it's not linearly independent. And that makes sense, right? I'm telling you that if it's a linearly independent set, then every single vector should give you different information. Does the 0 vector give you any different information? No, it doesn't give you any information, pretty much, right? Okay, so that's why we never want to put 0 in a set for linear independence, because it doesn't do anything. Okay. All right. So the next one is basically what I did at the beginning of class. It says that if you have at least two vectors, it's linearly dependent if and only if you can express one of the vectors as a linear combination of the others. All right? Isn't that what we did at the beginning? I said that if it's not linearly independent, so you had this equation, and it's not linearly independent, then one of these constants needs to be non-zero, or you can find constants that at least one constant that's not zero, and then you can solve. That was what I did here, right? Do I have a linear combination of the other vectors now? Yeah. So that's the idea. If, I'll just write it out down here so it's in the same spot. If your V1, V2 out to Vn is linearly dependent, then there exists C1, V1 plus C2, V2 out to Cn, Vn. Oops, I wrote my there exists part. There exists a linear combination here. I forgot a couple of words in there. There exists a linear combination of the zero vector with not all of the Ci equal to zero, right? Some of them might be, but not all of them, correct? In math, when it doesn't matter which one it is, we say without loss of generality. I'll talk about what I mean by that in a minute. Let's just suppose that C1 is equal to zero, or not equal to zero. Then I can solve for the V1 like I did last time. Notice the statement that I wrote here said that not all of the CIs are equal to zero. So I know one of them has to be non-zero. Well, I might as well just assume it's the first one, because if it's not, then I can just re-index, right? That's all the without loss of generality means. It doesn't matter which one it is, so I might as well just say it's the first one. So if the first one's not zero, then I can solve for V1, and now I have a V1's a linear combination of the other vectors, right? That's exactly what we said before, isn't it? That's one direction that says if it's linearly dependent, then I can express as a linear combination. Go the other way around. Well, if I can express as a linear combination, then all I'm going to do is just move everything to one side and have a linear combination that gives me the zero vector. Yes. Linearly independent says that if you have a linear combination that gives you the zero vector, every single constant has to be zero. Linearly dependent is the negation of that. So I can find a linear combination that gives me the zero vector where one of them is not zero. At least one of them is not zero. It's the negative of it. It's the negation of it. Good. Notice that part C here is just equivalent to part B. It's just negating everything, right? Okay. So part C says that it's linearly independent if I can't do that. It's the negation of the previous statement, right? And the last one here, I'm not going to bother writing anything for this one either. If you have two vectors, it's pretty straightforward to tell whether or not they're linearly independent, because if there's only two vectors and it's going to be linearly independent, one of them has to be multiples of each other. I can find a scalar times one of them to give me the other one. Okay. The reason for that is that if it's linearly dependent, I can write one of the vectors as a linear combination of the other, but If I only have two vectors, this entire side of your equation is gone, right? Because everything past this minus sign wouldn't be here; it would just be that, and I have a scalar multiple. Okay. All right. So when you have two vectors, it's straightforward, hopefully, to see that you really do have a linear you really do have a linearly independent or dependent set, or not, just by looking over whether or not there are scalar multiples. All right. We talked about how we figure out if a set of vectors is linearly independent or not. How did we do that? If we have a set, what did we do last time? In Rn in particular, how did we figure out if we had a linearly independent set or not? What was our technique? We did the same thing for spanning set. We just looked for a different thing when we were done. What was our big technique? Okay, so and why? Well, it wasn't necessarily we had more columns than rows. That was a case if we did have it, it wasn't going to work. But you're on the right track. How did we form the matrix to start with? Put vectors down the columns, and then what did you do? Row reduced. And for linearly independent, what did you look for? In every column for linearly independent, right? You look for a pivot in every column because you want to make sure you had unique solutions. And then, like Lennon said, if you had more columns than rows, then it's not going to work, right? You can't get a pivot in every column. Okay. All right. So what happens here? If you were to put, and we're going to write it out nicely here, but if you were to put those vectors in as columns, how many columns would you have? K. How many rows would you have? N. If your vectors are in Rn, you'll have n rows, right? Because you're going to write the vectors vertically. If you have more columns than you have rows, can you get a pivot in every column? No. So it has to be linearly dependent. That's the idea. Okay. Well, let's see if we can write it out nicely as a proof here. Okay. We're going to let C1 V1 plus C2 V2 plus Cn Vn equal the zero vector. If you're trying to show something is linearly independent or linearly dependent, you want to start with a linear combination that gets you the zero vector, right? That's the definition of linear independence. And then likewise, the definition of linear dependence. If it's going to be linearly dependent, then what do we need to argue? What has to be true about these constants if it's going to be linearly dependent? At least one is non-zero. We need to find a case in which at least one is not equal to zero, right? Okay. Let's think about setting up our vectors here. So for notation, if we suppose that our v sub I is the vector, pardon me, goodness, let's say it's, I'll use x's, x1i, comma, x2i, comma, out to xni, then what do we have to have as our system of equations? Well, I got to take this constant times the v1, this constant times the v2, and so on down the line, right? So if this is going to be a true statement, when I do the first components, I have to get 0. When I do the second components, I have to get 0 and all the way down the line, right? So then we have to have, what do we have? We have x11 c1. That's all right. Plus, what's going to be the C2? And the way I've got this labeled, I think I should have labeled it the other way around, but that's okay. The next one's going to be x21. This is the first component, right? And so I'm using, no, wait a minute. Sorry, I did label it the right way. This should be x1, 2 to x1n cn. That has to be 0. Likewise, the second components have to be true. All the way down to what? Yep. Oh, I'm using. Darn it. This isn't an N. My apologies. That's a K. That's my problem. I knew something wasn't right at the end here. Those have to be Ks. We have K vectors total. Okay. And then you're right. xn1, c1, xn2, c2, xnk, ck equals 0. What are we trying to solve for? What are we treating as the variables in this case? The K is the columns, the N is the rows, and what are we treating as the variables? What are the variables we would be solving for in this system? The C's, right? Because we're given the V's, correct? The X of whatever's are your coefficients. The C's are what we're trying to solve for, right? How many equations do we have? N. How many variables do we have? K. What kind of system do we have? Homogeneous system, right? This is a homogeneous system. This is a homogeneous system with n equations, and k unknowns. What happens in a homogeneous system when you have more equations with unknowns? What's true about the system? How many solutions do you get? Infinitely many. Why is that bad? What do we? If it's going to be linearly independent, why is that bad? Well, if we wanted this to be linearly independent, why is that bad? Because you don't have just one solution, right? You don't just have the trivial solution, correct? Good. All right. So this tells us that our original system, our original set, must be linearly independent. So in Rn, this gives you an easy way to look at a set and say, oh, there's too many vectors, it can't be linearly independent. Okay. So we have a few ways that we don't require a lot of work to determine if something is linearly independent. If the 0 vector is in there, it can't be linearly independent, right? If you only have 2 vectors and you can tell that one's a constant multiple of the other, can't be linearly independent. If you have too many vectors, can't be linearly independent, right? So we've got a few ways to be able to just look by inspection to see whether or not it's linearly independent. So let's look at these couple of examples here. We already did one last time. If we look at the second example, I know we set up the matrix, but using this theorem, we wouldn't have had to. We're in R2. How many vectors? 3. There's too many. It's not linearly, it has to be linearly dependent. It's not linearly independent. What's wrong with the first one? We got the 0 vector, right? This is not linearly independent. It's not, or you can say it's linearly dependent. Those mean the same thing. Since the 0 vector is in your set. Yes?
So, from a practical point of view, if you have a set of vectors, this is an easy way to find out if there is a solution instead of going through all.
Yeah. Yep, that's right. Yep. Now the last one here with P2, if we did our technique that we talked about last time, we would put them in columns of a matrix. Oh, well, if we did the technique that we did last time, I'm not going to write it down. If we try to put them down in columns, I'd have 3 rows and 2 columns. That doesn't tell me anything, right? There's not too many vectors. So, but in this case, how many vectors are in my set? There's just 2 vectors, right? Because there's just the 2 polynomials. So if it's going to be linearly dependent, we said that we could tell by if it's a scalar multiple. Are they scalar multiples of each other? Yeah. What do we need to multiply the first one by to get the second? 2. Okay. So since why are you not writing? What the heck? That's why I bring the extra. That pen is so finicky sometimes. So since the 6 minus 4x plus 2x squared is 2 times 3 minus 2x plus x squared. Oops. We see that set no, it doesn't want to erase. Fine. I'll just leave the mark there. Is linearly dependent in P2. If you were thinking about the other way, like we just came up with for Rn, we said that if the number of vectors was bigger than n, it was linearly dependent automatically, right? We didn't have to do any work. Is the same thing true for P2? If for P2, if I had 2 vectors, if I have 3 vectors in P2, is it automatically linearly dependent for P2? No, because think about when you fill out your matrix, how many rows do you get when you fill out a matrix for P2? You get 3, don't you? So what would be the maximum number of vectors that you could put in a set and have it linearly independent in P2? 3, right? Because remember, again, we have to have a pivot in every column. If you form your vectors by going straight down columns again, I fill a constant row, an x row, and an x squared row, right? I've got 3 rows, so I can get to 3 columns, I'm okay, but once I get to 4th, I'm not, okay? We're going to come back to that idea later. Well, now the other pen's working again. Of course it is. Why wouldn't it be? All right. Let's look at this next question. It says, what values of lambda make a linearly dependent set? Is it too big? No, not too big, so that's not a problem. Now let's think about what it means to be linearly independent again, okay? If I have a C1 times the first one, plus a C2 times the second one, plus a C3 times the third one, we have to get 0, 0, 0, right? That's what we're trying to solve. Agreed? What does this look like if I write it as a matrix equation? Not as an augmented matrix, but as a matrix equation. What would it look like? I've done this a few times now. What would I make for my matrix equation? Yeah, down the first column, yep, and then good. 1 on lambda, the constants here would be good. 0, 0, 0. Good. That's our matrix equation, right? It says we want linearly dependent, right? So we want infinitely many solutions. That's what the problem's asking for. if we want infinitely many solutions, what needs to be true about that matrix on the left-hand side? Think about it, the reverse question. If it were going to have a unique solution, if there was only the trivial solution, what would have to be true about your matrix on the left-hand side? If it'd be invertible, right? Okay, so we want this matrix to be not invertible, right? What's a numeric check for testing whether or not something is invertible? Determinant, right? So we want our determinant to be 0. We've done this a few times, haven't we? Okay. We agree? Okay. So take the determinant. We can do a couple of ways here. I'm just gonna just expand along the first row. So lambda times lambda 1, 1 lambda minus 1 times 1, 1, 1 lambda plus 1 times 1 lambda 1, 1. I know I did it quickly. This is going to be what? You have lambda times lambda squared minus 1 in the first one. The other one's just lambda minus 1. Right? The other one is 1 minus lambda. We agree? Okay. And equal to 0. So let's see here. I can be a little bit clever. That's lambda plus 1 times lambda minus 1. We agree? So now every term has a lambda minus 1 in it. We agree? The first one will be left with a lambda times a lambda plus 1. This will be a minus 1, and so will that because it's the opposite sign. Yeah. Like I said, this is a little bit clever. I'm nothing if not clever. This is, if you simplify it, this is lambda squared plus lambda minus 2. So that also factors as lambda plus 2 and a lambda minus 1, it looks like. So what values of lambda make it 0? 1 and negative 2. Good. Okay. So this is just another way to ask you to take a determinant, essentially. One of the reasons why I did this particular problem was just to kind of do a little bit of a foreshadowing to stuff we're going to do at the end of the semester with eigenvalues and eigenvectors. The process, okay, I know I was fast on the computations, but do you understand why we did... Oops, that was totally not what I wanted to do. Do we understand why we did this? I mean, if you don't understand why you did that, you can't do the rest of the problem, right? So again, here, essentially all we're doing again is setting up that matrix with the vectors as columns, and then realizing I need that to be not invertible. So when I row reduce, I need to have a pivot in every column, right? Say it again.
How did you realize that it didn't have to be, you didn't want it to be invertible?
Because if it is invertible, then I can move this to the other side and do the multiplication, and all I get is the 0 vector. And we want non-trivial solutions for linearly dependent. Yeah, that was why. Pardon me. Let's think about this next one without writing it down to start with. The first one, this thing says, if we have a linearly dependent set and I throw things, more things in it, I still get a linearly dependent set. Right? Why does that have to be true? What does linearly dependent mean again? I can get different. Yeah, I can get more than just one solution to the linear combination being 0, right? Okay. Well, if I can write 0 as a linear combination of these things and not use every constant to be 0, how would I write the 0 vector over here, do you think?
Same way, you just have 0 on everything.
Yeah, just put zeros on the rest of them, right? So if you have C1 V1 plus C2 V2 out to Cn VA, sorry, it's a K. CK VK is equal to 0 with not all of the CI is equal to 0, then C1 V1 out to CK VK plus 0 times the rest of them is still the 0 vector, isn't it? And still not all of the constants, not all of the scalars are 0. So the set has to be linearly independent, or linearly dependent, sorry. Again, think about it from an added information standpoint. Okay? The idea behind, and we're going to talk about it when we get to the next section, which may be after break. I want 10 minutes anyway. The idea behind linearly independent is that the fact that every single vector gives you information that the rest of the vectors doesn't. Okay? So for example, if you've had Calc 3, if you look at the vectors I, J, and K, the I tells you what the X coordinate has to be. The J tells you what the Y coordinate has to be. The K tells you what the Z coordinate has to be. And none of the other two can give you what the third one does. Right? That's the idea behind linearly independent. Okay? If it's linearly dependent, then one of these vectors gives me no new information. Well, if one of those vectors gives me no new information, same thing's here, right? I can get the same information to that one vector by using the other ones, is the idea. So there's not any reason to include it, right? It would be like using I, J, K, and then saying, well, I also need to use the vector 1, 2, 3. No, I don't. I can get 1, 2, 3 from I, J, and K. I don't need the 1, 2, 3 in there as well. Okay. That's the idea. All right. This last one has a little bit more of an application to differential equations, which is why I want to talk about it. Because this one's a little bit more, it has to do with a determinant too, so it's a nice application of a determinant. So it asks you to show that this particular set of functions is linearly independent in C infinity of negative infinity to infinity. Remember again, C infinity means infinitely differentiable functions, and the negative infinity to infinity part is the domain. So this is the set of functions that are infinitely differentiable everywhere. So sine, cosine, e to the x, all your polynomials, all those types of functions are in there. Okay. So again, if I want to show that it's linearly independent, we need to solve this and show what has to be true about the scalars. What has to be true about the scalars if we're going to solve that? If it's going to be linearly independent, what has to be true about the three scalars? They all have to be 0, right? So we're going to be a little bit clever when we do this. Since I have an infinitely differentiable, since each function is infinitely differentiable, I'm going to start differentiating. Okay? So let's take the first derivative of each of these. If I differentiate both sides, I would get C1 cosine x, right? Minus C2 sine x. I didn't do myself any favors by putting in something with a product rule in here. That's okay. C3 times sine x plus x cosine x equals 0. That would still have to be true. I'm differentiating. I differentiated both sides. The reason why I'm differentiating is because I know I can. Okay. It's a nice little trick. And you can do this for any of these things. Do it again. Since it's infinitely differentiable, I could do it infinitely many times if I'm going to stop after this one. This one's going to be what? It's a 2 cosine x plus, it's minus x sine x. It's 2 cosine x because the derivative of that is cosine, and when I differentiate the x, I'll also get a cosine. That's where the 2 cosine comes from. Now, why did I do it twice? How many equations do I have? I have 3 equations, right? How many unknowns do I have? 3. Now I have a square system, don't I? Okay. All right. That's why I did it twice. So I got a system of 3 equations with 3 unknowns. If I had 4 functions, I would do 3 derivatives. Okay. If you look at your matrix equation again, I know it's going to look a little nasty, but that's okay. I'm not actually going to do this, by the way. But this is how you would do it if you're doing something like differential equations. I did. There's my first one. There's my I'm just doing it that way. Yep. I'm taking off my coefficients. The functions now are the coefficients off the variables. All right. If it's going to be linearly independent, then what would have to be what would have to be true about this determinant? If it's going to be linearly independent, what has to be true about this determinant of this matrix? It has to be not equal to 0, right? So this will be linearly independent if this matrix is invertible. So if the determinant is not 0. Oops. Or if the determinant of the matrix is not 0. And when we have functions, we mean 0 all the time, right? The determinant would have to be 0 all the time if it's going to be linearly dependent. Okay. So how did we form this matrix? What's your first row? Just the functions. What's the second row? The first derivative. What's the second row? Second derivative. So when you have, and I'll write this in general, and then we'll stop for the day because I'm out of time anyway, I think. Yep. All right. So if we have a set of functions, f1, f2, out to fn, which is a subset of our C infinity, this, this set is linearly independent if and only if the determinant of the following matrix. So I use my first row is just the functions. My second row is the first derivative of the functions. And keep going until we do the n minus first derivative. Is not equal to 0. And actually, the way that a lot of mathematicians write this is this way. That means it's not identically equal to 0. What that means is it might be the case that the function is 0 at some point, but it can't be 0 all the time. Identically equal to 0 means that if you did this determinant, everything would cancel out. That's what identically equal to 0 means. We refer to this determinant, it has a name, it's called the Wronskian. Oops. And the reason why I'm talking about it, besides the fact that it's a nice application of linear independence and something that's other than just Rn space, this comes up in differential equations. Okay? When you want to look for solutions to differential equations, you want things that write the solutions uniquely. In order to be unique, you need linear independence. To check that your solutions are linearly independent, you can do this. And I know many of you either have taken or are taking linear or differential equations. Okay. So the general rule here is that if you've got n functions and you want to show that those n functions are linearly independent, you form this square matrix. It needs to be squared to take the determinant, right? Form the square matrix, take its determinant, and get something with still x's in it. Okay? You don't want everything to cancel out. This wasn't the best example because I didn't want to take that determinant. Okay? All right. Have a good break, everybody. We will see you on a week from Monday, the 24th, I guess it is. All right. If you're traveling, travel safely. Enjoy some rest.